Good morning, this is Sunil. So today we have come to a place called Satanur. This is about 80 kilometers from the city of Bangalore. So today we are here at a farmhouse slightly away from the town of Satanur. So here we have tried to adopt a few sustainable practices in terms of energy, water, waste management, nutrition. So let me try to walk through all these interventions that we have done here. To start with, this is our solar PV system. As I have told before, there are three major parameters we consider when you talk about sustainability: energy, water, nutrition, and waste management. So we have done a little bit of all of these here. So let me walk through a few of them as succinctly as I possibly can. So this is, of course, first we start with the solar PV system. So this is a solar PV system here to actually power the loads of this farm. This is slightly little more than 3.5 acres with mostly farm and some kind of trees around. So this 9.6 kilowatt off the grid PV system powers our main house. Most of the loads in the main house is actually catered by the solar PV system. We have a granary, we have a storage unit, we have other ancillary stuff here, like some few small farm equipments, which are all powered using this solar PV system. This is a 9.6 kilowatt off the grid PV system consisting of 16 panels of, this is TOPCon monoperk bifacial panels. So this actually powers the system. And why we are doing the off-grid system? There are few major reasons. Off-grid system, in my opinion, is the most sustainable way of actually meeting our energy demand. Why? Because we are generating our power right at the on our rooftop and using it right here. So the production happens locally, the consumption also happens locally. Second, and equally important, is when we connect it to the grid. When we want to try to do a hybrid system, or when we actually try to do a dynamic ESS system, they are always connected to the grid. So the problem with connecting it to the grid is sometimes, particularly in these slightly far off places, the grid distortions also get into our inverters and to our loads. To insulate our inverter, to insulate our load from any kinds of grid distortion, it's actually better to go in for an off-grid system. And when we are looking at reliability, particularly when it is slightly remote, it is better to be off the grid because we are eliminating one variable, that is the distortions and any kind of surges and spikes from the grid. So these are the three main important reasons that why we actually try to choose a fully off-grid system. I'll explain the off-grid inverter and the working of it when we actually go into the inverter panel. But this is about the solar panels here. So we have got 16 panels. They are bifacial panels. You can also see we have actually tried to paint the roof white. This again has a few main reasons. One is to actually keep the house below cool. So that way the electrical energy demand of the house also goes down. So the energy demand for cooling reduces. As you can see, these are all bifacial panels. Okay, sometimes they are actually called glass to glass modules. So they can also pick up some amount of energy from the reflected light, technically called an albedo. So a white surface reflects slightly more amount of light. So this is another reason why we actually paint the roof white. Of course, white roof also increases the rainwater runoff, thereby increasing the yield of our rainwater harvesting system. So this is one part of the building. On top, we have actually populated the entire roof using solar panels. So this is by and large powering the entire farm in terms of their energy requirement. So we'll just go down now. I'll show you some electrical parameters and some technical parameters in terms of off-grid solar PV design and explain the inverters and other kinds of accessories that we have put there. And then I will take you through some amount of other intervention like biogas and rainwater harvesting and things like that. Let's go down now. So now this is our main electrical room. Solar panels are on the top. So we have connected all the panels into this electrical room. Let's go and see inside. So as I told you, most important maintenance, all the maintenance required for the solar system actually is written and pasted here. So and of course we have a fire extinguisher, safety, very important. So let's see our electrical infrastructure here, like what we have done. I'm not going to go too much into details about or technical details about any of this. Just I'm going to explain and give an overview of the system. As I told you, it's a 9.6 kilowatt system. So we have two charge controllers, charge controller 1 and 2. Each one of this can take 5 kilowatts. So we have split the system into 4.8 into 2, that makes 9.6 kilowatt system connected to two charge controllers, and we have got two inverters. Of course, for each of the charge controllers, we have got DC-DB or all the DC protections. On the AC side, we have got the AC controls and the AC protection, and we have got the battery isolators, one for the negative side, one for the positive side. We have got two batteries here. You can see there are two batteries connected in parallel. These are two lithium-ion batteries. Each is 175 Ah at 46 volts. These are from a company called Newnham out from Bangalore. So we have 16 units of energy being stored in these batteries, and we also have a 9.6 kilowatt solar PV system, and these are the electrical infrastructure. Now, very briefly, let me open up this wiring system for you, and very briefly, I'm going to explain the technical aspects of this off-grid power system. So let me just open these boxes and then resume. So now these are the elements of the off-grid system. So as I told you, we have got two charge controllers, two inverters. So let me explain very briefly. I'm not going to go into more details, more technical details about the components as well as its functionality. But basically, we have, as I told you, we have got 9.6 kilowatt, 4.8 into two systems. That 4.8 kilowatt is further split into two strings. So this is for one 4.8 kilowatt system, this is for other 4.2 kilowatt system. They call this as a DC distribution box. So since even that 4.8 kilowatt is done into two strings, we have got two fuses on the positive side, two fuses on the negative side. There's always a spare fuse. We have a SPD. Since the voltage is coming around 200 volts, we have got a 250 volts DC SPD. We also have a DC isolator or a MCB. So for each 4.8 kilowatt system gets into these two boxes respectively. The output is given to our charge controllers. This is charge controller number 1, charge controller number 2. These charge controllers can take a maximum of open circuit voltage of 250 volts. So this string design has been done with this as our main parameter. 70 amperes is the maximum amount of current in amperes that this can actually push into our inverter. So this is our charge controller, and now we come to a very important parameter of our design, that is the battery. Since it's a completely off the grid PV system, so the night loads are met only by these batteries. So there are two batteries, each of 8 units, or what we actually call 8 kilowatt hour into 2. So 16 units of energy is there in this in these batteries. These are actually lithium-ion batteries from a company called Newnham. So these are actually automotive batteries repurposed for our ESS design. So there are a few interesting things about the battery and the battery design per se. One is highly sustainable because they're all repurposed. Actually, these are the cells, EV cells, which are actually done their first life, and then they have come into our solar PV design. So, in fact, these batteries are actually very conducive for solar kind of purposes. There are other added advantages because since they are automotive batteries which have gone into the EV infrastructure, they would have gone through very rigorous testing, and the thermal parameters are actually very high because they would have gone into very sophisticated testing process, and they would have gone into the automotive industry. So the cells have already gone through a lot of rigorous testing, rigorous vibrations, rigorous in terms of their thermal runaway and their thermal designs. So when it comes to our solar system, the batteries, the cells automatically are very rugged and very robust. So now we have got two batteries and they are parallel. So you can see these are the positive sides of the battery. There is a wire run from each of the positive terminal to the positive isolator. And we have got negative terminals. Two wires are coming into our negative terminal, and there are individual bus bars here. There are now positive isolator, negative isolator, and we have a bus bar. From this we have got a connection into our MPPT charger as well as our inverters. I'll come to the inverters in a while, but these are very, very important. Battery isolators are very important. Plus, over and above, we also have couple of battery switches here. So there are a lot of communications. I will not go into details of all this communication. There is CAN, and there is also an IoT device here which communicates the battery health to the cloud, so we can monitor all the parameters of the battery through this small IoT device. Now we come to our inverter. So the inverter is also taking. There are cables from the inverters to the battery, and these are technically hybrid inverters. They can also take power input from the grid. However, we have not connected the grid here. So this is our ACDB box. I will just come to this. But as you can see here, if you can come close by, there is something called as AC in. You can see here AC in, that's the input from the grid. There are no wires here. We are not even connected. The same thing on this side also, we have not connected any input from the grid at all. So this runs completely off the grid. This inverter, this is from a company called Victron. It's a Dutch make. The charger and everything is Victron. So these are actually very, very sophisticated inverters. They can be actually used for dynamic ESS purposes. They can be used for grid feeding. They can be used to optimize the energy between grid, battery, and solar. But for this particular application, we have actually kept it simple. We have just not connected the grid at all. So this works like completely like an off-grid system. When it comes to the AC infrastructure, you can actually come here. So this is the grid side. You can see just switched off. So the grid actually power comes here, and then there is a ELCB, there is a type 2 SPD, there is a MCB, and this power is supposed to go in as input to our inverters. As you can see, there is no cable here. By design, we have not kept it. We have kept it off, or rather we don't have any cable there. So the output from our respective inverters are actually combined here. You can see these are the output from the individual inverters. We again have a surge protection for the output as well. We have a circuit breaker, and for emergency we have given a changeover switch. In the event that there is some fault with the inverter, we can always bypass and run the loads from the grid. So we always say bypass. Don't give input to the inverter. You can bypass. See, now I can actually physically close this. Now I put it off. See, the loads have gone off. And now if I pull it down, I can run out of the grid power. So this is given only as a fallback or as for emergency purposes. But by default, all the loads are always run by solar. So if I put it up, the loads get shifted to the solar power. So this is a general overview of the system. Of course, on the load side, we have some protections. We have got multiple circuit breakers for multiple loads here. This is for safety and for any kinds of maintenance purposes. And we have got another box, an earthing junction box, because there are multiple earthings here. The battery negative sometimes has to be grounded, and we have got body earthing, we have got the DC side earthing, we've got the AC side earthing, we have got the surge arrestor earthing, surge arrest on the DC side earthing. So all the earthings is basically terminated in two different bus bars, and we have got about 5 grounding points around this building. So these are about the major component in the overview of the system design. There is one more most important component here. we can come and see here. This is, they call it, they call servo. Basically, it's a data logger come, it's kind of a, what you can say, the brain of the system. All the communication essentially happens through this. You can see here is the same device. It's called servo. Basically, they have n number of ports on both the sides. So basically, all the communication, all the integration happens in this box. For example, we have got two MPPT controllers. So how does this MPPT controller communicate or communicate with each other and communicate with the cloud? It happens through this servo. You can see here, each one, it's called BE direct cable. This is the communication protocol. Each of these cable is going one into MPPT1, one into MPPT2. So this is how the communication, intercommunication and communication with the cloud happens through these cables. And we also have a power cable. This is powered by a 48-volt system. It's connected to the battery here. And then we have a main internet cable. The internet cable is coming through this modem. We have a CAN communication here. This is the CAN cable at the back that is connected to our battery here. This is the CAN communication. This is an internal communication between the batteries. And we have something called as a BE bus communication, that is communicating between the inverters and from inverters to our servo. So this is another communication protocol. So all these communications are actually terminated here. You can actually also connect a HDMI cable to actually view it in an external device. So this is a very, very important component when we are designing a system with Victron. So this is a very, very broad overview of the system here. Again, the maintenance. The one part of the system is just installation. The second system and the most important system is maintenance. How do you maintain the system? You have to keep the panels clean. You have to keep the inverter area well lit, well illuminated, well ventilated, and keep this and all the boxes, all the batteries dust free. And you have to make sure that there are no rodents or any kinds of dust around the electrical room. So this is about our electrical design in terms of an off-grid solar PV system. Again, a general overview. We have got boxes for housing all our components. These are called DCDB, two numbers. We have got two MPPTs, two inverters, two isolators, two batteries, and our ACDB. So this is about our electrical panel and our electrical design. Now we will go and see how a little bit of waste management and how we are actually trying to be a little more sustainable even in terms of cooking energy requirement. Just step outside and take a look at that. So this is about our solar PV system. Let's go in and look at our biogas system now. We'll just close it up. So now we saw the solar rooftop panels on the roof. We saw the electrical infrastructure, inverters and all the other controls. And this is a biogas plant. In a course of time, cattle shed is going to come here. So this is going to be used to digest the waste generated in this property as well as some amount of cow dung. So this is a biogas digester. I have shown the videos before as well. This is a conventional biogas digester. All the cow dung and the other food waste can go here, and this digests that waste and converts into usable methane, and this is actually used for cooking purposes. So the gas generated from this digester goes into a filtration unit. As I have explained before, there are some amount of impurities in our gas. So we have got water which can dissolve some amount of carbon dioxide. We have got a desiccant, it's activated carbon, it's nothing but activated charcoal, and we have a steel mesh. So the gas generated passes through all these filtration unit and gets into the kitchen there. So we have a stove there where the gas is used for cooking. So the staff quarters is meeting most of their cooking gas requirement by this biogas digester. We have a pressure block here. This is just to increase the pressure of the gas. If we take this out, the pressure of the gas gets reduced. It's just that's a counterweight to actually increase the weight so that the gas is under pressure. So this is about a few things in done here. We have got solar, we have got biogas, we have some the recharge wells and rainwater harvesting system. So this is about all the systems here. So sustainability, as I told earlier as well, is about three major components: energy, water, nutrition, and waste management. If all of them are like internally and locally addressed in terms of production and consumption, we can be far better in terms of our sustainable initiatives and carbon footprint and in the overall scheme of sustainability. So thank you very much. Okay, so we saw about the solar panels, we saw the electrical room, we saw the electrical infrastructure and the solar arrangement, but there are a couple of more things that are actually equally important or rather more important than solar energy. That's about the efficiency of usage of the energy. So I'll just touch upon a few things on that. So this is the main building, the main loads of the house are actually here. So I will just tell you a couple of things about the energy efficiency considerations while designing a solar system, or in general about the efficiency. As I told you, efficiency is actually far more important than electrical stuff itself. So let's just get in and I will show you a couple of interesting things here. There is rainwater harvesting system here, there is gutters, there are rain chains, the water collected actually goes into a well there. We will talk about the energy efficiency now. So now coming to some design elements, you can see the house is actually very well designed. There is good natural ventilation, natural lighting inside, and as I told you, see, look at these fans. These are BLDC fans. These are extremely energy efficient. These are the fans. They are LED lights, and there's also a quadrangle with natural lighting. Again, as I told you, there are BLDC fans which are very efficient. So efficiency is as important as generation of solar energy. Like, you know, we always say, try to avoid energy usage. If you can't avoid, try to minimize. Then after these two parameters, then we look at generation of solar energy.